13 asks for the maximum acceleration attained on the interval from 0 to 3 by the particle whose velocity is v of t equals t cubed minus 3t squared plus 12t plus 4. So we have the maximum acceleration, so for starters we should get the acceleration function. We know acceleration is the derivative of the velocity, so let's derive. We get t squared deriving to t cubed deriving to 3t squared minus 6t plus 12. So that's our acceleration function. We want to find the maximum of that function on this interval from 0 to 3. So here's two candidates right here. So we need to find a of 0 and a of 3, but we also need to check out wherever the derivative of a is equal to 0. So we need to go one more derivative, right? In other words, we need to find the critical numbers for the acceleration function. That would be 6t minus 6. So we can see that that's equal to 0 at t equals 1. So there is our third critical number. So we're going to plug 0, 3, and 1 all into the acceleration function because we're interested in the maximum acceleration. Well, a of 0 is easy because we're going to get 0 minus 0 plus 12. So there's a of 0. A of 3, that's going to be equal to 3 times 3 squared minus 6 times 3 plus 12. 3 squared is 9, 3 times 9 is 27, so we have 27 minus 18 plus 12. 27 minus 18 is 9, plus 12 is 21. So a of 3 is 21. And finally we need a of 1. Right, so when we plug 1 into the acceleration, we have 3 times 1 squared minus 6 times 1 plus 12. 3 minus 6 is negative 3, plus 12 is equal to 9. That is definitely not the highest value. We want the maximum amount. All right, so that means we're looking at that value right there of 21. Our answer is D. All right, in regards to number 14, we're now into the related rates part. The radius r of a sphere is increasing at the uniform rate of 0.3 inches per second. Okay, so we see radius increasing at this value, radius changing. So in other words, dr dt is equal to 0.3 of an inch per second. Get that on the screen there. There we go. All right, we want to find the rate of increase in cubic inches per second in volume. Okay, so that means we're interested in what is dV dt equal. Okay, we're given one more piece of information. We're given that the surface area is 100 pi square inches. So the surface area is 100 pi. All right. So we need dV dt, which means we need to start with our volume. So V equals 4/3 pi r cubed, because we're talking about the volume of a sphere. Okay, and we're going to take the derivative, which we've done a bunch of times in class and on the homework. V derives to dV dt. 4/3 and pi are coefficients, and r cubed derives to 3r squared dr dt. Now we've done this multiple times where we've crossed out the 3's. And when we cross out the 3's, we are left with 4 pi r squared dr dt, which lo and behold happens to be the 4 pi r squared part, our surface area. All right, so this dV dt is actually equal to the surface area times dr dt. We're just subbing 4 pi r squared out and the surface area in. All right, and the surface area, we're told, is 100 pi. So this is equal to 100 pi times dr dt. But we were told dr dt is 0.3 of an inch per second. So the 100 and the 10, well, the 10 crosses out and it eliminates one of the zeros. So we can see there that we have 3 times 10 times pi, or 30 pi, as our solution. 15 is rather tricky. we have ourselves some similar triangles right here. We have a light post and a person, and they're both walking. So what's happening here, or excuse me, the person's walking, but they're creating two triangles. All right, similar triangles here. We have the small similar triangle, which I'm going to outline in black ink, and then we have the large triangle, which is in red. All right, they're similar because of the angle-angle theorem from geometry class. Now, what do we know? We know that the person is 6 feet tall. We know that the street light is 15 feet tall. And the question is, at what rate is the shadow lengthening? So we can see the shadow right down here. So we're trying to figure out at what rate is this changing. So let's just make that equal to, well, let's do this. We've got, we'll make that x. Okay, because we're trying to, so that means we're trying to find dx dt. That's the rate at which the shadow is changing. Okay. Well, we need to come up with a little bit more information. We see here that the person's walking away from the street light at a rate of 4 feet per second. Okay. Now, here's the person. Here's the lamp. And the rate of this side right here is changing at 4 feet per second. So we don't know how far away the person is at the moment, so we need another variable. Let's call that y. Okay. By calling that y, we now know that we can assign the 4 to dy dt, because the person is walking 4 feet per second away from the light. So dy dt is 4. Dx dt we don't know about, but we do know that the person is 6 and the lamp is 15. Now, what formula do we use? Well, as I mentioned a moment ago, these two triangles, the big red one and the smaller black one, are similar triangles. All right, that means that their sides are proportional. So in other words, the bottom of the small triangle compared to its vertical side is equal to the bottom of the large triangle compared to its vertical side. So what does that mean? Well, actually I'm going to put it right over here. What it means is that the bottom to the side, or x over 6, that's equal to the bottom of the entire triangle, which is x plus y, to 15. Okay. There's our equation. Right? The sides are proportional. X to 6, and you could do x over x plus y and 6 over 15. There's different ways to put it, but we're going to work this one out. Okay. Now, what do we do after we get our formula? We derive it. Okay, so we're going to derive this equation. I'm going to change this ever so slightly before we derive it. We have x over 6, which is the same thing as 1/6 x. All right, and then we have x plus y over 15, which is the same thing as 1 over 15 times x plus y. Now we kind of get the coefficients a little clearer, so when we derive it, we know that 1/6x derivative will be 1/6 dx dt. And then here, 1/15, that's a coefficient, so that stays. And then the derivative of x is dx dt, and the derivative of y is dy dt. Okay. Now, we have to solve for dx dt, and we know that dy dt is 4. So, what do we have here? We have 1/6 dx dt is equal to, now I can distribute the 1/15, so I have 1/15 dx dt, and then over here I have dy dt, which I know is 4, so I'm going to sub 4 in, but I have to multiply it by 1/15, so I have 4/15 right there. Okay, lots of fractions here, and that's annoying. So why don't we do something to eliminate those fractions? What's a common denominator between 6 and 15? Yeah, it'd be 30. So let's just multiply everything by 30. Okay. So when I multiply 1/6 by 30, 30 and 6 goes into 35 times. So I'm going to be left with, I'm going to move right over here. I'm going to have 5 dx dt when I multiply this term by 30 equals, now I have 1/15 dx dt times 30. Well, 15 goes into 30 two times. So this will be 2 dx dt. And finally, 15 goes into 32 times. So again, 15 goes into 32 times. And 4 times 2, that would be 8. All right, subtract 2 dx dt's from both sides. So 3 dx dt is equal to 8. And therefore, dx dt, which is what we're trying to find, is 8 over 3. 8 over 3 as a fraction is 2.6, repeating.